Hi, this is Mr. Mitchell with a video about energy. Now, energy is the ability to cause change. So without energy, nothing would ever change. So what makes energy? Well, it's work, and we've studied work. Like work, energy is a force that's given over a distance. So energy is work. And you can probably guess what the unit of energy is. Just like with work, it is joules. So energy constantly transfers from one object to another. Here, the tennis ball transfers its energy to the racket. Up down here, a person transfers energy from her body to the pencil when they write. And here, the wind transfers energy to a flower as it spreads across the field. So there are several different types of energy, and every one of them can involve a transfer, or they do involve a transfer, and every one of them could be calculated in joules, the actual energy that is done. Here we have mechanical energy. For example, a person's legs push on a bicycle pedal, or a person's hand directs a hammer. Mechanical energy is purely physical energy. We have the transfer from the legs to the wheels and from the hand to the nail, but it's purely physical. Here we have some examples of chemical energy. Say we have an automobile's gasoline. The gasoline transfers energy to the engine, and that's what makes it go. Or here we have a person that is eating food, and the food's calorie help fuel our body after it goes through the digestive system here. So a chemical reaction has taken place in both of these examples, and that's why it's called chemical energy. And yes, energy is transferred, and energy can be calculated in joules. Electrical energy. A person turns a light on in a room, and the electrical energy comes through the socket, through the wire to provide the light. Same concepts happens with the cell phone. You have energy, you have work that is happening, and it's electricity that provides that energy. So all of these examples include work, energy transfer, and the energy transfer can be calculated in joules. We have terms here called kinetic energy and potential energy. I think you've had this before, but as a reminder, energy in motion is called kinetic energy. And as you can see in the examples, we have a girl who's in motion, we have a ball which is in motion, it depends, and we have something less mechanical, but we have energy that is flowing into the lamp and energy that is happening here with the logs being on fire and things moving up in the air. So we have kinetic energy, that's actual energy that is happening. But you can also look at it a different way. We have potential energy in a lot of things. Energy is not always in motion. You have stored up energy in what's called potential energy. For example, if you have a stretched rubber band here, then you have potential energy. I mean, you're just a let go away from that going to fly, and that work and energy has happened. Same thing with the gasoline that is pumped in your car. That gasoline represents potential energy. And even an apple on a tree represents potential energy because it can fall and work or energy will happen then. And in fact, you can even calculate the potential energy of something that has to do with gravitational pull, because you know the gravitational constant, you can figure out what that is, and we'll get the formula on a different slide. Now we have something I want to talk about called the law of conservation of energy. Total energy remains constant, whether we're talking about an object's kinetic energy or potential energy. That's the law of conservation of energy. Consider a roller coaster. It has high potential energy up here at point A. In fact, I looked up, and the potential plus the kinetic energy for each car is about 110,000 joules. So as that potential energy is released down here in B and C, it's going very fast. So actual motion is kinetic energy. So it has a lot of kinetic energy at C, but a lot of potential energy at A. But the total amount of energy stays the same, 110,000 joules, no matter where it is. Even though speed is slow here and fast here, you don't go over that 110,000 joules. You have the same amount that is stored up in potential and in actual energy. Now, in reality, we're going to lose energy on this roller coaster. It's going to have the heat from the rails touching the wheels. It's going to have the friction from the air resistance. I mean, just the fact that there is air in front of it that it has to go through means that it's not going to have the same amount of physical energy. It's not going to have 110,000 joules in the car as it comes back up, but some of it is going to be lost in the heat on the track, and some of it will be lost to the friction, but it would still have the same amount in the whole system. Same thing here with this girl who is swinging. She may start out with 400 joules, and if she swings and doesn't put any more energy into it, it's going to stop. But all that energy, that 400 joules, remains. It's not just built magically into the air. I mean, it goes to the friction of the wind that is in front of her, the air that's in front of her, and back here where these are connected to the bar, it's going to lose energy to heat there. It takes about 10 joules down here to do Newton's cradle. The energy goes here to hits here through all of them and goes up. Eventually it will slow to a stop, and those 10 joules will look like they have been spent up, but they haven't really. You have the air resistance that is between them and whatever heat that happened to be between them hitting each other. So you still have what scientists would say is a measurable amount of energy in the entire system. So that is one of the important points there. Right. I hope you learned a little bit about energy.